Now we're going to talk about putting together a lot of what we've looked at so far to see how to put equations and functions into matrix form. This is a really important topic in linear algebra, and one that often isn't covered very much in introductory classes. Remember, a lot of our reason for using linear algebra was to write expressions and functions more compactly in matrix form. So it's really important to be able to take complex-looking expressions, things with a lot of sums or many different indices, and write them more succinctly in matrix form. Now, it's often easier to go the other way, to take a matrix expression and just apply definitions to get a longer expression that has explicit indices and references explicitly the different parts of elements. But going the other way can be somewhat trickier, and there isn't any good precise set of rules for covering all these circumstances. Rather, it's best to just go through a lot of examples and gain a good intuition about how to put functions and expressions in these simpler forms. We're going to go through 3 examples here and see how we can take a seemingly complex expression and put it into a simpler form. Okay, to start off with, let's look at the following problem. We're given a set of vectors AI, where here each AI is a vector in Rn, and a set of BI, where each BI is a scalar value, and we have each of these things from I equals 1 to m. So we have m different vectors here and m different scalar values here. We now want a function f, which will take as input vectors in Rn and return scalar values. In particular, the function is defined as follows. So we want to take f of x, so take inputs x, and compute the sum from I equals 1 to m of the inner product of ai and x minus b. Take this whole thing and square it and add these things up. The question now is, how can we write this thing a little bit more compactly without having to include this sum here and many different indices into the i's and b's, etc. So to first start off with, we'll note that suppose we had some vector, y I'll call it, where yi was just equal to this term. So yi was equal to ai transpose x plus bi. Remember, here this is a scalar value because this is an inner product of 2 vectors of size n. And this is another scalar, so this yi would be a scalar value. So y really here would be a vector in Rm. In that case, this function would simplify to the sum from I equals 1 to m of yi squared, which we know from the past video can also be written as y transpose y, or in fact even a little bit more simply, as the squared L2 norm of y. This is just a definition of the squared L2 norm. Okay, so that's great, but how do we actually come up with this vector y that has this property here? Well, if we form a matrix A that has all these AIs as its rows, so A1 transpose will be the first row, A2 transpose the second one, etc., all the way to AM transpose. Then if we multiply this thing by x, that would give us kind of the first portion of this vector here, right? Because this would give us another vector where the first element was A1 transpose x, the next was A2 transpose x, all the way down to AM transpose x. And so that would be the first bit here. So erasing that for a second, y will first equal a times x. Or maybe I'll write this again up here or down here. A, remember, is this matrix where each item here is a row of A. Okay, so that takes care of this first term here. This would now be a vector y where we just had each element being A, I transpose times x. And to get this other b, oh, sorry, this should be minus b here. To get this other element bi, well, now we just define a vector b kind of very simply here. B will just be the vector of all these bi terms, so b1, b1, b2, all the way down to bm. And if now y equals ax minus b, then we have exactly what we want here. The ith element of y is equal to ai transpose x minus b. So to sum things up, this whole thing here can be written very compactly as just the 2 norm of ax minus b squared, where a and b are defined like this. The nice thing about this form here is that it doesn't have a sum, and we can represent all of it just with one matrix vector multiplication, subtracting another vector, and then taking the 2 norm of that.